So before we actually start the class, what I wanted to know from you guys is that is it a one-way traffic where I'm just telling you guys something and you guys are forced to believe that, or you guys think that whatever we are learning in the class that is actually useful? And you can be as honest and as candid as possible. That's okay, because my reason or intent for asking that question is to see or find out opportunities where I can do better as a teacher. So anything that you guys want to share?
It's useful, but I'm taking AP pre-calculus, not just regular pre-calculus, so some of the things I do are a little bit more advanced than what we do in the class.
Okay. That is good information. Okay. Dave and Chris. So yeah, I mean, as this class is designated for pre-calculus, that's why I'm covering or trying to stick to the premise of the syllabus. And obviously, regardless of whether you guys are taking AP pre-calculus or calculus or pre-calculus alone, if there are any doubts with respect to any particular topic, you guys can just let me know a couple of days in advance so that I can prepare and talk about those concepts also. So anything that is bothering you, I mean, in the math space, obviously, if you ask me questions on biology, I'll flunk big time. But then within maths, up to college level, if there is something that you guys would want me to teach or explain conceptually, with a 2-day notice, I should be able to do that. Okay. I'm planning to start a calculus batch also. I mean, so right now I'm doing preparation for that, because whatever I'm teaching you guys, this is something that I've learned 35 years ago or maybe 30 years ago. So I have to just brush up all the things that I have studied in the past and just align that with what you guys study here, and then we'll start. Okay, alright, that was the prelude of this class. So simple messages: if there is anything that you guys need any help with outside the class also, within maths boundary, please don't hesitate to send it to me and we'll work together on that. Okay. Now, we have covered till unit 5, which was on conic sections. So starting today, we want to start unit 6, and that is vectors. Now, before I start jumping on vectors and scalars and those stuffs, what is the understanding that you guys have with respect to vectors and scalars? In a conceptual term, don't give me any mathematical jargon. I just want to understand what is the concept behind that. What is your understanding of things? If you just wake up in the morning and somebody says, okay, tell me what is vector, and you know that that person is not a math champion, if you have to explain that, how would you explain that? What is a vector, what is a scalar? Any initial thought? Chris?
I'm trying to make my definition as less math oriented as I can, but it's just a quantity that measures the magnitude or the size of something and then the direction it goes in.
Okay.
And then I'm not sure about what scalars are.
Okay. So I'll simplify that for you guys. If you are measuring something that has magnitude, meaning some absolute value, and a direction to it, that is vector. When you only have magnitude, no direction, that is what is scalar. Yeah. Now let's jump onto this topic. So let's look at some real-time day-to-day scenarios that we deal with. Now, if I say that you guys have to come to the class, okay, then you will figure out what are the means to come. Will you take a bus? Will you ask your parents to drive you to the class? I know for Dave and Chris it might not be easy. Chris, you are in DFW area, right?
I'm in Chicago.
You are in Chicago, okay, wonderful. So Chris and they both are in Chicago, so they'll have to take flight. They cannot drive if they have to come to the class. Prisa, I believe, is in DFW, so she would probably prefer to drive if there's a reason for her to come to the class. So now, when you're driving, you will say, okay, I will take a car which drives at 70 miles per hour. And Dave and Chris, they will say that, okay, I will take a flight which flies at 500 miles per hour. And depending on the distance, you know how many hours it will take for you guys. Now, in both the scenarios, this is what I'm talking about, which is the speed. This is the speed of the car and this is the speed of the flight. So far, we have only looked at just the speed part of it. So, is it going north? Is it going south? And this is another thing that I have a big confusion with. Okay, people say travel 5 miles and then go north. Which way is north? I don't know. I know left, right, front or back. Which way is north? I don't know. If I'm standing in a place, if somebody says, okay, go north, I would be utterly confused. But anyway, that confusion is out of the syllabus. We'll not go there. But here, what I'm trying to say is, we are just talking about the speed at which it is moving. Now, if we start talking about, let's say, speed in this direction versus speed in this direction or speed in this direction, that is when the speed gets renamed to another thing called velocity. So, when you talk about speed, you are totally blindfolded with respect to the direction in which you are going. When you talk about velocity, you are forced to think of the direction in which you are traveling. Okay? So, let's look at some of the very commonly used things that we talk about. If I talk about moving something from this place to this place, which is, let's say, 5 meters away. So I had, let's say, a block which I moved from here to here. If I just say how much I moved 5 meters. This is the distance. I'm only talking about the distance between my origin and my destination. If I at all dare to think about the direction in which I'm moving, am I moving from here to here or am I moving from here to here? Meaning when I append that direction information along with the distance, that is when distance, so if I put that in mathematical terms, if I say distance plus direction equals displacement. None of the dictionary will give you this calculation, right? That distance plus direction equals to displacement. This is only for us to relate things mathematically. So when you have a distance in mind and you add a direction also, say distance in which direction? Are we talking about going north? Are we talking about going south? Are we talking about going to the east? Are we talking about going to the west? So how much distance in which direction? When you put these two things together, then you don't have to say distance plus direction. You can as well say my displacement is 5 meters towards the right or towards the left or whichever direction we are talking about. So this is the first example when we encounter with this term which has distance plus direction. So distance is my magnitude. Is it 5 meters? Is it 500 meters? Is it 5,000 meters? Or miles, whatever it be. If I'm only talking about the amount, the quantity, without worrying much about the direction in which it is being calculated, that is your distance, and when you add the direction to it, that becomes displacement. So distance here is nothing but scalar. When we're talking about the scale, see, look at this little carefully. This is sounding something similar to a scale. What does the scale do? If you're looking at a scale, it just tells you this much is 1 centimeter, this much second 2 centimeters, this much 3 centimeters, 4 centimeters, likewise. So this just tells you the length or the magnitude of the length. Yeah. So when we are only talking about only the magnitude part of it, without worrying about the direction, that is scalar. When you include direction into your consideration, it is vector. I think I have beaten this to death by now. You will not have any confusion with respect to the difference between scalar and vector. Is that a fair statement? Okay. So basically, we are talking with respect to distance plus direction becomes displacement. Likewise, now you will say, okay, fine, 5 meters I am traveling in 5 minutes. Okay, 5 meters I am traveling in 5 minutes. So what is my speed? 1 meter per minute. Okay, that is still the speed. It has only the magnitude part of it. It just tells this is the speed, which is 5 meter by 5 minutes, which is 1 meter per minute. This only tells you the magnitude. Now you have all the flexibility in life. You can go north, south, east, west, or northeast, southwest, whichever direction you choose. You still have your speed defined. There's no direction to it. That's why this is scalar. As soon as you add direction to it, saying that I'm traveling in north at a speed of 1 meter per minute. Now you are talking about the magnitude or the speed appended with the direction, and that becomes velocity. So these are some of the two most commonly terms that we encounter or we deal with almost on a daily basis, right? I mean, you talk about if you have to go to school, then you would take two things into account: at what speed I'm walking and in which direction I'm walking. If you don't keep the direction into mind, you might end up landing in Walmart instead of landing in school. Yeah. So that's why though it's not the appropriate example here, but what we are trying to depict here is that when you look at speed and the direction together, that is called velocity. So any travel, any tour that we plan, we always plan that where we are going to go. So you say, okay, this is going to be my speed and I'm going in this direction. This is my destination. So that is how velocity comes into existence. So these are two very commonly used examples of vector and scalar quantities. Are we clear, or you want me to scratch my head further and lose few more hairs? Are we clear?
Yes, sir.
Okay. All right. So losing hair is a very practical example because that's what I do in a very predictable way. So that's why it was relevant here. But anyways, coming back to the point. So now let's look at some practical examples. So if I say something like this, that okay, let's say I'm representing velocity here. Or for now, be velocity, be whatever it be, I will just call it a vector. So if I am representing something like this and just showing the arrow, I'm certainly showing the direction here. What I'm not showing right now is the magnitude part of it. If I put something like 5 meter in this direction, now it's a complete or well-defined vector where you have magnitude and you have direction to it as well. If I represent something like this and say 30 miles per hour, I'm certainly displaying the speed and then compounding that with the direction. So this is a vector. So every vector you will come across, you will see two parts to it. One is called the magnitude and one is the direction. Now the way vectors are represented, you will see that okay, fine. Let's say A is one vector. How they write it? Okay, A is a vector. So it has some magnitude and has a direction. If you have to get the absolute value of the vector, meaning just this part, just the scalar part of it, this is how you represent that. So mostly when you talk about the mod of something, right? Mod of x, you're talking about be it plus x or minus x. I'm just taking the absolute value and knocking off the sign. That is how you represent this one. In terms of vector, it is represented a little differently, like what you see on the screen right now. Yep. So this is just the representation part of it. And how do we represent a vector? Now I'll give you guys few examples, okay? And let's see how do you interpret this. 3 meter per second. 3 meter per second, 5 meter per second, So between these three vectors that you see on the board right now, this one is 3 meter per second. So this is, here we are trying to probably depict velocity, right? So I have speed and I have direction. Here also this is a velocity, speed and direction. Here also it's speed and direction. So this is also velocity. Between these three, if you have to say, and I will put one more. And let me give few names to them. So this is, let's say this is my vector A, this is my vector B, and this is my vector C, and this is my vector D. So between these four vectors, if I ask you guys, do you think any of the vectors are same, or what is the reading from these four vectors? Let's say if I talk about vector A, you will say that this is a vector where this is depicting velocity 3 meter per second in this direction. This one is depicting 5 meter per second in this direction. Looks parallel to this one. And third one is also looking parallel to this one. So direction seems to be same. This is also 3 meter per second. This one is 3 meter per second, but this is horizontal. So between these four, if you have to find out which two are same, or do you think any of the vectors are same? The question might sound lame, but there are two vectors which are same. Okay, tell me what is your thought process here and why you think so. And it's an interactive class, okay? So I would want to hear your point of view because I have one intent here, okay, for asking this question. That's what I'm asking. So between these four vectors A, B, C and D, where A, B and C are parallel, meaning same direction, but these two have same magnitude, this is a different one. And this has same magnitude but direction is different. So between these four, do you think any two vectors are same?
Would it be A and C?
Okay. How about you, Chris and Dave?
Yeah, I was thinking A and C would be the same.
Okay. Chris, how about you?
Yeah, I agree.
Now I want to confuse you guys. So here A is starting from this point, C is starting from this point. Okay, so they both don't have the same starting point, and the arrow that you see here, these are called terminal points. So the starting point and the terminal points are not matching for A and C. So how come you guys believe that A and B are same? And the answer is very simple. Trust me, I'm just picking your brain a little bit.
Because of the length.
I'm sorry?
The length.
No, length is... No, my question is this. I'm saying that you guys said that A and C seem to be the same. Okay? Because they have same direction, same magnitude. But my counter argument here is that A and B both have different starting point and different terminal point. Then what is the reason that you think that these two are same?
Does the starting point and the terminal point play like a big role in them being similar? Because from what I remember, isn't it just the same magnitude and direction that makes them the same?
So if this question was for a lottery ticket for $100, I would have given you $100. So you are spot on. So see, again, I was trying to re-emphasize this thing that when you talk about vector, since the beginning of the class, and I'm pretty sure all of you have encountered with this term vector, what it keeps on saying is the magnitude and the direction. So my question on the starting terminal point is actually invalid, because you will say that my primary definition or my only definition of a vector is it is magnitude and direction. I don't really care what the starting point is, what the ending point is. As long as my magnitude matches, as long as my direction matches, there is no further discussion. I'm trying to enforce this and make it solid in your mind that you will never ever think about or worry about the starting ending point, like what you said, Prisha, okay? That in case of vector, we are only concerned about the magnitude, meaning the scalar value of it, and the direction. As long as these two criteria are matching, we are good. Make sense? Chris, Dave, I'm just asking you guys to promise me that you will not worry about these two things in future ever, because vector is only about magnitude and direction. Yeah.
Okay, sir. Understand.
Yeah. Okay. Now, so in that case, let's look at let's visualize this against a graph. So if I have that vector like this and a vector like this, and this is, let's say, 10 miles per hour, and this is also 10 miles per hour, and both have the same direction, magnitude same, I will not even care. Okay, these two are same, these two vectors are exactly the same, because what matters is the magnitude and the direction. As long as these two are matching, I am going to be least bothered about it. Yeah. Now you will say, why do we need to think that way? So that essentially takes us to the next part of the topic around this one. Now let's look at a vector and its components. And let's say I am made of 5 things, or let's say my fist is made of these 5 fingers, and this fist is also made of 5 fingers. When you will think that these two fists are congruent or same, when all my 5 fingers match. Yes, meaning these are the 5 components of both of my feet. As long as all these 5 components match for both, between both the hands of both the fists, you will believe that these two are same or congruent. Same way, let's understand how do you break down a vector into components. What exactly do you mean by components of a vector? Let's break the vector into components, and then if we have to compare 2 vectors, if we see both the components matching, we are good. Make sense? All right. Now let's look at this vector, which is, let's say, "50 miles per minute." So I don't know which vehicle I'm talking about. I'm saying 50 miles per minute. So in 1 hour it will probably go almost like 3,000. Yeah, 3,000 miles per hour. And if we have a vehicle like that, we can all reach India in 2 hours. That will be fun. But anyways, that fun will park for now. Let's look at this as a number. So 50 miles per hour per minute. This is a vector that I'm representing right now, and this is a direction for us. Now when you say component, what do we mean by that? Any thoughts? Okay, so you guys are a little more shy than me, and I take it, that's fine. You guys are like small kids for me. Okay. So now this was my vector. How do I want to visualize that? I would want to break it down into 2 components, and I will call them as my x component and my y component. Meaning this vector, if I visualize this like a right triangle or right angle triangle, whatever you call it, I can always look at visualizing a vector along the x direction and the y direction, and then think of this like a right angle triangle, where this one I will call as the x component and this one I will call as the y component, or you can call it differential, you can call it increase, you can call it run and rise, whatever way you are comfortable. So every vector you can break down into horizontal and vertical component. And those are called the components of a vector. So this vector, any vector, let's say this is a vector. What I will do is, I will just draw a line here, and from here, from the starting point, I will draw a horizontal line, and then from the terminal point, I will drop a perpendicular on that line, wherever it meets. This becomes my horizontal component or the x component, and here to here becomes my vertical component or y component. Is that okay so far? So now, every vector, you can, if you just look at this, let's say 5 miles per hour, and you just know the direction, it tells us that this is going in a certain direction. But in a two-dimensional plane, when you are visualizing this, you will always think that, okay, this is my starting point, this is my terminal point. Can I look at this as what is my horizontal element and the vertical element to this vector, or the horizontal and vertical component to this vector, so that I can try relating that in a two-dimensional plane. I can think of visualizing this on a graph with my x and y coordinate. Now let's add some more element to it, and now let's visualize this in a coordinate plane. Now if you look at it, in the coordinate plane, this part says how much you are moving in x direction, and by reaching the terminal point, how much you have moved in the y direction. Or it's a run and rise. So how is your vertical component changing for every change of the horizontal component? So in geometry, in algebra we talked about the slope of the line. In trigonometry we talked about the SOHCAHTOA. In geometry we talked about right angle triangle. All that, right? Everything is coming together now. So this vector that we're talking about, if you visualize this in a coordinate plane, you are essentially talking about how much your x value changing, or how much is your y value changing, how much your vertical movement is happening for every movement of x, or the slope of the line, whatever you call it. Yeah. So then, if you look at this, what you will say, okay, how much is my y changing? Let's say this was, let me do one thing. Before I go to the next level of discussion, I will put it along this one. Now let's say my origin point and the origin of the coordinate plane are coinciding, so that we have this whatever is the value of this thing, this is my x component, and whatever is this value is my y component. So every vector you can always think of looking at getting the x and y coordinates or the horizontal and vertical component to locate a vector. So if somebody gives you a vector like this, you'll say, okay, fine, what is my coordinate of this point and what is my coordinate of this point? Or what are the x and y component of this point and what are the x and y component of this point? As long as you get that value, you will be able to find out what is your, how you can plot your vector in a plane. Are you guys with me so far? Yeah. So now, just look at this vector. If you are talking about a vector, whatever be the case, it is eventually translating into or looking like a right angle triangle when we want to visualize this as an x and y component. And as soon as you realize that this is a right angle triangle, Uncle Pythagoras comes into life. And then we apply the Pythagorean theorem, where we will say, if this is, let's say this is, if I call this as magnitude of the vector, okay? So my magnitude of the vectors will be equal to delta x square plus delta y square, or this will be square root of this. So now if you look at this situation, there is nothing new that we have learned. What we are saying is, I can locate a vector, assuming to start from origin, if I know what is my x component and y component, or I can find out the x and y component if I know the magnitude and the direction. So here, this is your direction. This says in which direction this vector is, right? So when you are given a vector as an example, they will say, okay, it has magnitude of 50 units, be it miles per second, be it or be it 50 miles itself, distance miles, in the direction 30 degree to the north from horizontal axis. So 50 miles 30 degree to the north of horizontal axis. So this is your horizontal axis, 30 degree north. So you are making a 30 degree angle, and then 50 miles. So you have the magnitude here. So this is 50. So if you have to find out the x and y component, there are different ways you can do it. Since you know this is 30 degree, then you can also apply Sokato, basic trigonometry, which says, okay, if this is 50, let's say this is x, this is y. So x by 50 will be equal to how much? In Sokato terms, x by 50 will be how much? Sine of 30 degree. If this is 30 degree, and sine of 30, we know that x by 50 will be equal to sine 30. Sine 30 is 1 by 2. So x becomes 50 by 2 or 25. So just by knowing the direction and the magnitude, you are able to derive what will be your. I should have not said x to this one. I should have said y to this guy, so that I would have not created confusion for you guys. So here it will be y by 50 equal to this, or y by 50 equal to this, or y will be equal to 25. So here, just by knowing the magnitude and the direction, you are able to find out the vertical component of the this thing as of the vector, and so you can apply. This will be like x by 50 will be cos 30 degree, and then you can find out the value of x or the horizontal component as well. Is it making sense so far? Dave, Chris, are you with me?
Yes, sir.
Okay. So now let's do a double click on that, and not every vector starts from origin, right? So your vector could lie anywhere. So if I'm talking about, let's say, a vector like this, which has, let's say magnitude as m. I'm just saying m, okay? So if you have to find out the components, and you are given that the direction is, this is, let's say, 45 degree. So then you have to find out the horizontal and vertical component. And here, this is, now since we are visualizing this in a coordinate plane, I will say, let's say this is my x1, y1, and this is my terminal point is x2, y2. So we are not starting from origin, and neither the terminal point is on the origin. Okay? So if you have to find out, this will be your delta y, your vertical component, right? Because your terminal point always, see, in though we are relating this with the coordinate plane, but in scenario of when you're talking about vector, you're always talking about this part. So we'll use the knowledge of coordinate plane just to derive what is my height along the vertical axis and what is my length along the horizontal axis. That's all. We will not we will not relate with x2, y2 or x1, y1 like a regular coordinate plane. Just from understanding point of view. Okay? So that now if you look at how much is my x component changing in case of this vector, what is my horizontal component of the vector? Obviously you will say here is x2 and this is x1. So the horizontal distance is x2 minus x1, and similarly the vertical component is, this is y2 and here to here is y1. So this distance is y2 minus y1, which we are calling as delta y. Okay. So up to this much is okay, right? Are you guys with me so far? I'm just trying to help you guys visualize that when we are talking about a vector, it would not necessarily start from the origin, or the origin of the vector will not be coinciding with the origin of the coordinate plane if you visualize that within a coordinate plane. So what will be your vertical component? That will be nothing but the difference of the y component of these 2 points, and the what will be the horizontal component? That will be the difference of the x component of the starting and terminal point. So here in this case, when you are talking about finding out the x and y component, see, so now my vector m, I will say, is nothing but my x component, which is delta x, and my y component, and then I have a direction which is 45 degree or whatever it is, in the north of this one, north of the horizontal axis. So basically my whole vector is identified by this and the direction. My x component, meaning how much is my horizontal component, how much is my vertical component, and remember these two are just the absolute value. Just the absolute value as in without looking at the unit. You might have positive or negative. Now let's look at another vector. Let's say this starts from here to here, and this is x3, y3 coordinate in the coordinate plane, x4, y4. If I have to find out this vector, same thing will apply for this guy also. What we will be concerned about is what is the angle and what is the difference between x4 and x3, y4 and y3. So let's say this is m2, this is m1, this is m2. So this will be, again, let's say this is delta x1 and delta y1. Delta y1. And then the direction. So the point that I am trying to make here is, my vector, any vector has two components. As long as I am able to find out the horizontal and vertical component, I am looking at the absolute value, how much is my x value changing and how much is my y value changing. That is what goes with my x and y component. And the angle. So look at this one and this one. Let's say in both the cases the angle is same and is showing the direction also same. Both are 45 degree and going upward. So your delta x, which is this part, and this part is matching. Imagine if your arrow was changing from here to here, what would have happened? Your x4 minus x3 value would have been flipped. It would have become x3 minus x4 because the direction starting point to terminal point, right? So you subtract terminal minus starting. So here, this is a terminal point, this is a starting point. What is your x component? Your delta x here is x2 minus x1. So let's say if x2 was 8 and x1 was 6, you got 2. In this case, if I look at, even if the magnitude is same, but my x component is what? Let's say this one was 7, 4, and this is 7 comma 4, and this is 5 comma 3. Okay. So here what is happening is your x component is terminal minus this one, the starting point. So in case of this one, it is terminal point is 5 and your starting point is 7. So terminal minus this. What do you get here is minus 2. What do you get here is 2. So what I'm trying to demonstrate here or depict by all that I've been doing for last 5 minutes is that in case of the vectors, what is of relevance here is the direction and the magnitude both. Even if I have two vectors with the same magnitude, when I visualize this in a coordinate plane, my x component reverses when my direction reverses and plus becomes minus. So is the case with the y component. Let's say if this one goes here, right? Or yeah, I mean again, I don't have to worry about moving this vector itself. Here we have one in the positive direction, one in the negative direction. It has positive slope, it has negative slope. So what's happening is in this case your x value is increasing. So your delta x is positive. In this case your x value is decreasing. Your delta x is negative. So your whatever the component has changed. So that is why here, because of the direction, even if you visualize a vector on a coordinate plane, you clearly see that just because of change in direction, my delta x value or the x component value has changed from positive to negative. So that is why any vector that we think about, there are two parts to it, the magnitude and the direction. When my magnitude are same, this length of the line is same, then also if the direction is changing, my x component value is changing. So would be the case with my y value also, because here my y value is higher, it became lower. I mean here it is higher, it became lower. Here it was lower, it became higher because of the direction. So if you put the things together, here when we talked about the description of or definition of a vector, we said okay, vector means magnitude and direction. Now when you visualize the vector on a coordinate plane, you see that okay, vector means you can break it into two components, horizontal component and vertical component, and mathematically you can see that when your one vector is going upward, other vector is going downward, even if they have same magnitude, your x component is actually in this case increasing, in this case is decreasing. So is the case with y component. Here in this case when it's going from this side to this side, y component is increasing. Here when it's going this way, your y component is also decreasing. So that means a direction is playing a very crucial role when you look at comparing two vectors in a coordinate plane also. So this is more of a mathematical alignment of what we understood as a concept for vector, and this is how you can relate mathematically or quantifiably. Let me stop here. Any questions? And there is no question as a dumb question. I would love to hear if you guys have any questions. No? Or did I just ran through it very fast to get you guys baffled? Prisha, Chris, Dave, anybody? Are you guys clear about what I said or you're not?
I guess.
Okay. Alright. So basically, if you look at what we have covered so far is these three things, okay? I will probably not try going into the next topic, and let me see what all I have planned and what all we have covered. Okay. So let's do a quick recap of what we have learned so far, and then based on whatever time we are left with, we'll see what we can learn more. So first thing we understood or started with our understanding of what is a vector and what is a scalar, and we kind of re-emphasize that, okay, when you're talking about a vector, you're talking about a magnitude and a direction. Be it in terms of distance, which becomes displacement if you add direction to it. If you're talking about speed, add direction to a speed becomes velocity. There are two classic examples that we deal with very often. Now, the next thing that we talk about is, okay, fine. Does the starting point matter in case of vector? And the obvious answer is no, because your vector is always looked at from two perspectives. One is the magnitude, the exact value of the vector, the length of the vector, and then the direction of the vector. So starting point doesn't play a role. Whether you are starting from origin 0, 0 or you are starting from a coordinate point, a point on the coordinate plane 4, 3, doesn't make a difference as long as the magnitude and the direction both are matching. Then we learn about what do you mean by component of a vector. That is where we learn about how do you break down a vector into horizontal and vertical components, and how do you visualize that. And then we tried relating that with the original concept of vector means magnitude and direction, and that is where we saw that if you plot a vector in one direction versus the reverse direction, meaning the upward slope versus downward slope, with the same magnitude, with the same direction, but it's going, one is going upward, one is coming downward. And that is where we saw that how is my x component changing in the first case versus the second case, meaning what is the difference between my origin point and the terminal point, meaning terminal point minus origin point's x value and terminal point minus origin point's y value. So we saw that when my direction is changing or reversing, it goes from positive to negative or negative to positive. So that re-emphasizes the fact that these two vectors will not be considered same because their components are different, right? So if I, without confusing you guys, if I just take a example of two vectors, okay, this, let me put it this way. So this is this going this direction, this is 2, 3, and this is 6, 8, and I have another vector which is, let's say 3, 1 and 7, 5, let's say 6. Okay, so here if I look at this vector A, okay, now what is my delta x? Let's say this is B, this is A. So I'll say delta x A, delta x B, delta y A, delta y B, or I'll probably put these two things together so that we don't get confused. Okay, so here what is my delta x here? Let's assume that the both have same angle, both are parallel. Okay, so I'm not going there. Now, what is my delta x A? Meaning for this A, what is my delta x? So my delta x or the x component or the horizontal component is terminal point minus origin point. So 6 minus 2 x value. Delta y is again terminal point minus origin point. So 8 minus 3. So this one becomes 4 and this one becomes 5. In this case, this B case, what is my delta B? This is my origin point, this is my terminal point. So terminal point minus origin point, x component. Terminal point 3, origin point 7. So 3 minus 7, which is minus 4. Y, what is my vertical component? Terminal point minus origin point, y component. So terminal point is 1, origin point is 6. 1 minus 6. So this becomes minus 5. So in this case and this case, this case and this case. So if you look at A, your horizontal component is 4, vertical component is 5. In case of B, vector B, your horizontal component is -4, your vertical component is -5. Even if both have same angle, both are parallel to each other, they have the same magnitude, your components are not matching. So going back to my example of the 5 fingers that I was showing you guys. So out of the 2 components, let's say my 5 fingers are equivalent to 2 components. Here and here, these are not matching. This one is positive, this hand is all positive, this hand is all negative. They will not be the same. They should not be treated same, because that goes against the definition of the vectors, and we see it mathematically also, that you will never ever dare to say that okay, 4 is equal to -4. Yeah. Do you guys agree? You don't agree? Okay. Now, one last thing, and that is pretty much relatable, just because it was part of the plan today. I will just probably take 2 minutes and let you guys go. This was that vector magnitude from graph. So, let's say you have a graph, okay, and you have the x and y components given. X1, this is x1, y1, and this is x2, y2, and you have this line, and you know this is the angle given. All you have x1, y1, x2, y2 value given, and you have to find out the magnitude. It is as simple as converting this into a right angle triangle and applying Pythagorean theorem. You will find out the difference of these two. X to get the horizontal component, you will get the difference of y to y1 to get the vertical component, and depending on if it is this way, you know that you will find out this minus this as x component, this minus this as a y component, and then once you have the x component and y component, okay, you got 2 values here. So this, you got this value as your x component, I mean the x component of the vector, and you got this value as your y component of the vector. What is the magnitude of the vector? Simply x component squared plus y component squared. Magnitude equal to square root of this. Now you will say, do I have to really worry about it's going upward or downward? Magnitude is magnitude. Speed, when you are saying 50 miles per hour, you are not saying 50 miles per hour or negative 50 miles per hour. It doesn't matter actually. And so would be the case mathematically also. Let's say your delta x you are getting 6 or you are getting -6. Does it really matter? No. You are doing a square of that. Delta y, if the difference between these two is coming as 5 or -5, does it really matter? No. Because you are anyways doing a square of that. So that's why when you are deriving the magnitude, regardless of the sign that you are getting by subtracting from terminal point to the origin point, you will get the same value. Okay. So meaning what I am trying to say is your magnitude doesn't change whether you are going upward or downward. As long as the difference or your horizontal component and the vertical component's length are matching, you are good. Did I rush through it very quickly, or this was done in an understandable way?
Could you repeat that a little bit? Just like a little bit.
Okay, so it's very simple. Now, if you're talking about magnitude of a vector, what you're talking about is a vector which has the origin point and ending point, correct? So if you have to find out the magnitude, essentially you are trying to find out the length of this line, correct? Line segment rather.
Okay.
This is your starting point, this is your ending point. And by the definition of the vector, we have realized that we just call this as a delta x, or the horizontal component, which is the length of this line, and this is called delta y, or the length of this, or the y component, correct? And this is nothing but, this length is what? This whole length minus this length. So this is your delta x, horizontal length of horizontal component in this vector. Similarly, what is this length? This is this length minus this length. So you will get the delta y, delta x by subtracting the x coordinates value for the terminal point minus the x coordinate of the origin point. Similarly, you will get the delta y by subtracting y coordinate value of the terminal point minus y value of the origin point, and then you will get this one. What I was trying to say toward the end was that whether this is going up, so you get x2 minus x1, or it's going down, where you get x1 minus x2. It will not matter because we are anyway doing a square of that. So if you are going up, your x value increasing, this will be positive. If you are going down, the same value, the difference will turn out to be negative. You are going from higher value to lower value. But when you try to find out the magnitude, the sign doesn't matter, right? I mean, whether it's a 5 square or 6 or minus 5 square, you'll get the same value by doing a square of that. Correct? Did I?
Okay, yeah, that makes sense.
Yeah? Okay. So that brings us to the end of the class. We covered quite a few lessons. We covered, I think, 3 lessons from this unit. We have in total 9 lessons in this unit. So what I would request you guys is, whatever we did for last 1 hour, just don't watch the video of this class. Just pick up Khan Academy, go to pre-calculus, open up unit 6 and try doing the unit test for first 3 chapters. Okay, it will not take you first 3 lessons. It will not take you more than 20 minutes, I would say, if you have understood the concept. If it takes more than 20 minutes, that means either I did not do a good job, or you have to probably spend some time watching the video to revise if you are missing something. Yeah, and if these 2 options doesn't work, we will have a class next week. All right.